Namaskar. Hope you all are doing well. So in today's video, we are gonna talk about k-means clustering. This comes under the umbrella of unsupervised learning. In unsupervised learning, k-means clustering is like most famous algorithm. And in today's video, we are first gonna look at the internal working and mechanism how k-means clustering works. Then so in second part of the video, we are gonna see k-means clustering live in action. So for k-means clustering, we can use both R and Python, but one of my friend has requested to do it in R first. So what I'm gonna do, I will be doing this k-means clustering both in R and Python. First, we are gonna do it in R. Then later on top of the same template, I'll be creating Python template as well. Let's jump into the concepts of k-means clustering. Let us look at first how the internal mechanism of k-means clustering works. To understand the internal mechanism of k-means clustering, we will take a sample data. On top of that sample data, we will try to apply k-means clustering manually, and we'll see how the result turns out. So right now in front of us, let's imagine a 2D coordinate system, x and y axis. In this coordinate system, we will try to plot our sample data. So here I am trying to plot my sample data. Uh, with naked eyes, it looks like this sample data consists of 2 or 3 clusters, but I mean, this dumb machine doesn't know that there are clusters in this data already. So using k-means, we will try to tell the system this is how you think and this is how you process if at all there are any clusters in your data. So to move further, what we will do, we will try to identify 2 random points here, like I have identified here. The one is red and another one is green. So consider green as a green cluster and red as a red cluster. To proceed further, we will identify 2 random points on this coordinate system, point 1 and point 2. In next step, what we will try to do, we will try to calculate the distance of point 1 from the green cluster and distance of point 1 from red cluster as well. So to calculate this distance, I mean, we can use 2D coordinate geometry formula, and this is an Euclidean distance, by the way. So this is how it turns out to be. We will calculate d1 and d2. So this distance, it's like we have 2 random points in a 2D coordinate system, and we are trying to calculate a random point, how much it is far from these 2 points. So let's do some maths on top of it. Clearly d2 is greater than d1 if at all we have to look it from distance perspective. If we do some maths on top of it and we try to plot it on a number line, this is how it will be. This is our point 1 and this is our d1 and this is our d2. Clearly d2 is greater than d1. So this is how it works. So if any point is more near to the green cluster, we will assign it to that cluster. Right now, point 1 is more near to d1. So we will assign it to the green cluster. This is how it will be. We will change its color to the green. Now point 1 is in green cluster. Similar exercise we will do with point 3. Again, we have identified a new point on the coordinate space. This is how it is, and we will repeat the same process for this point as well. We will try to calculate the distance from the 2 random clusters points which we have identified, the red and the green, and we will again find out the distance. And since it's more near to green cluster, we will assign that okay, this belongs to green cluster. And the point which we have to take in account here, that the green cluster and red cluster initial point what we have taken is a random point actually. Again, so this is how it will look if we do it in an iterative process way. This is how it will be. So it's like we are assigning each and every point to what cluster it belongs. This is how it will be. In first pass, we have calculated all the points to which cluster it belongs. Right now in front of us, there exist only 2 clusters, red cluster and green cluster. So what we will do next, we will try to again calculate the centroid of the new clusters. For example, in this case, our new centroid for cluster will be somewhere near to this. So this is how the centroid has moved. Now with this new centroid, we will try to calculate distance of each and every point again, and we'll see if some other points can be assigned to another cluster or not. And this process we will repeat until and unless there is no change in point allocation to different clusters. For example, again, if we move forward, in this case, if we look at this point, looks like D2 is again less than D1. To be more precise, D1 is greater than D2, in other words. So this point is now more near to red cluster. So what we will do, we will assign this to red cluster again. What has happened here, earlier this point belonged to the green cluster, but the moment we moved our centroid to the new position, now this point belongs to red cluster. So in this iterative process, we will do it until and unless there is no further change in points from one cluster to another cluster. And to start with, these cluster points will be random. And how many clusters we will have in a dataset, we will specify in our code. Now, whatever theory we have seen just now, we will try to do the same thing using our R code and Python code as well. First, we will try to do the same thing with R code. Then I will replicate the same with Python. So now let's jump into the Python and R code. To save time, I have already created an R template for k-means clustering. The packages which we are going to use here is the scatterplot 3D for 3D plotting, of course, and it will follow tidyverse, cluster, and facto extra. These three packages are super helpful if you are working with k-means clustering. You can directly install it from cran. It's available there freely. Now going into our coding, so what I have done here, I have already taken the iris dataset. It's already available in R, so it's like most famous dataset if you are working on machine learning. So it's just like on a data variable, I have assigned the iris dataset. It's just a summary of that data, but I'm trying to print it here. And using ggplot library, I am trying to visualize the data in a 2D geometrical form. Basically, by using colors, I'm trying to segregate between the types of species the flower has. And if we plot the same if we plot the same data in a 3D environment, this is how it will be. Looks like it's taking time to running. Yeah, here it is. So if we plot the same data in a 3D plane, this is how it is. The difference to notice here is that if we plot the data in a 2D sphere, this is how it is. If we draw a line from here to here, we can only separate out this in two clusters. But the moment we draw the data in a 3D space, this is how it is. Looks like there are three clusters in our data and they all can be separated like this. It's very clearly visible from top view that okay, these are the three clusters here. This is what we are trying to achieve using k-means clustering. We're trying to identify as many clusters as possible to an optimal level. So in next step, what I'm trying to do, I'm just dropping the name column and I'm reading only first four columns. The last column includes the species name, so I'm just dropping it because k-means can be applied only on numeric columns here. So I will just rerun it. Yeah. So in this section here, I am trying to scale the data. Scaling here is very important because the different columns of data are in on a different scale. So using the scale function, which is available in R by default itself, just have to pass down the data frame and it will scale accordingly. Also, you can define your own custom scaling functions also. But right now, for this data set, our scale function by default, which is available from R, is more than enough. So right now I have a scaled data. I'm just trying to print 5 rows of out of it. Right now, if you see our earlier our data was like this 5.1 4.9, and now this has been converted into this. Basically, it has defined a range. So this is when I try to print out the summary out of it, this is how it will be. Sepal length, sepal width, petal length, petal width. This is how the new maximum and minimum has changed. Also, next step is to how do we calculate the distance. To calculate the distance of different observations, we will use the get distance function from the package available itself. And the package, it's already available in facto package actually. So you just have to use it. Uses Euclidean distance in backend, so it will calculate the distance out of it. And here I'm trying to visualize whatever the distance I have calculated. If you don't understand this graph, it's all right. If when we will plot the k-means diagram, you will be able to relate how different clusters are helping in visualizing the data set we have. So next step is to, this is a really crucial step to understand. In line number 74, what I'm trying to do is, this is the scaled data which we have. On top of this scaled data, we will be using, by default I'm supplying two clusters, and the number of times the random points it will try is 25 times. This you can supply according to your need. I mean, different combinations needs to be tested out on different dataset. For this dataset 25 worked, and number of clusters initially I'm passing as 2. The moment I pass it on, let's run it. Using str, I am trying to print all the columns it contains the result of k2, of course, and k2 is nothing but the output of k-means function. And if you have to understand this output, this is how it is. This cluster contains this observation 1 is to cluster 1, observation 2 is to cluster 1. That's how it is. So all the records from 100 to 150, they are now assigned a cluster, either cluster 1 or either cluster 2. Similarly, this size refers to the distribution of clusters we have. We have 1 to 2 clusters which are divided into ratio of 50 is to 100. Now, we are trying to visualize the clusters here. Yeah, we are trying to visualize whatever our k-means data has given us the output. The k-means output which we are using here is the k2, the output from the earlier function, and the data is this, the data skill, the skill data, of course, not the original data. And we are just trying to visualize it right now using two clusters. This is how the data looks like. But wait, can I apply more clusters on top of it and visualize the result? Let's see how it is. So here I am passing center 3, that means it will have 3 clusters, and number of random points which it will try is 25. Number of random points, if at all you have to understand, just go back to theory part and watch it one more time, because it's really crucial to understand that initial points in cluster, k-means cluster, you put it at random points and you try out different points, whether it is working, whether it is not working. So that's what it has to try 25 times. That's what I'm trying to tell the code itself. It's intuitive, by the way. I mean, you don't have to apply much brain thanks to our packages. Yeah, so now here I'm trying to visualize the data using 3 clusters. That's how it is. They look more separable in this way. Now let's try with 4 clusters. Again, I'm just trying to replot it. This is how it is. Again, same thing. I can do it with 5 clusters as well. There it is. And let me just plot it. This is how it is. Now the question here comes is like, what is the optimal number of clusters which can be, accommodated in this data set and which doesn't disrupt our data set also. So to identify the optimal number of clusters in a dataset, there is an elbow method which we generally use. It's like most famous method in k-means always. So what we will do, we will try to plot the sum of a square errors relative to what the number of clusters are given. For example, here what I'm trying, look at this graph. So on x-axis we have plotted number of clusters, and on y-axis the total sum of a squares. So it's like, uh, in this graph, wherever you find the elbow is like there is a sharp drop in total sum of a squares. If we look at 3, between 2 and 3 there is a sharp drop in total sum of a squares. So we will say the ideal number of clusters exists, I would say 3 or 2 maybe. Sometimes we will have to take decisions on our perception. So I feel 3 would be the most ideal clusters in our case. So that's how you identify the optimal number of clusters basically, and that's how you drill down which is the most suitable number of clusters for us in this data set, of course. So this is an overall view of how we will be using R to perform k-means clustering. Next video will contain the Python template of the same dataset and k-means clustering done on top of it. So till then, namaste.